This question is called coupon collection, and it says there are n distinct types of coupons in cereal boxes, and each type, independent of prior selections, is equally likely to be in a box. So there are some boxes. In each box, you can get like one coupon, and each box may either repeat the previous coupon or get you like a new coupon, right? And there are like many different types. There's like n different types of coupons, right? Part A asks if a child wants to collect a complete set of coupons with at least one of each type, how many coupons or boxes on average are needed to make such a complete set? So saying how many boxes do we have to open to get all n types of coupons. So we're trying to find the expectation, right, of x, like how many we have to open to get all possible types. What we can do is we can treat each, we can look at it like coupon by coupon, and treat each coupon as its own geometric situation where you want to get the probability of success for each coupon type, and then take each probability of success, convert it to an expectation, and so you can sum across the expected number of boxes you have to open across all coupon types, or across all the coupons you have. So, or you could obtain. So let me break that down for a sec. So we're saying we're gonna break it down coupon by coupon. So K is how many coupons so far, coupons you have so far, right? We're gonna solve the expected number of boxes you must open to find the next coupon, given you have K already. And we're gonna do that across all K. So, so if K equals 0, we have 0 boxes coupons so far. Then for the next, the chance of getting a new coupon in the next box will be n over n, right? Because we have none so far. So when you open the next box, you're guaranteed to find a new coupon type. Okay, which equals 1. And it's n over n because we're saying it's possible for us to obtain any one of the n box coupons out of the n coupons. And then for geometric geometric distributions, the expected weight to obtain this situation for success basically is going to be 1 over p. So this is the probability. So the expectation will be 1 over p. In this case, is 1 over 1, which equals 1. If k equals 0 or k equals 1, we obtained this coupon. To get the second coupon type, the probability will be n minus k, or n minus 1 over n, right? We're saying we can get the probability of getting the new one, right, is the chance of getting any of them except the one we already pulled. So it's possible to get any of them except that one, and so the probability is n minus 1 over n. Same thing, the expectation of this will be 1 over p, and that'll be n over n minus 1. You can keep going, like k equals 2, you're going to get n over n minus 2, right? And we can basically sum across all of them. So we can say the expectation of x is 1 plus n over n minus 1 plus n over n minus 2, etc., all the way to n over 3 plus n over 2 plus n over 1, right? If we just flip that, right, we're going to get say like going from this way to that way, just flip the order, like from right to left. We're gonna get it equals. This is already the answer. We're done, but we're just gonna make it look better. It'll be like n over 1 plus n over 2 plus n over 3 plus n over n minus 1 plus 1. And we can factor out an n. So it'll become 1 over 1 plus 1/2 plus 1/3 plus whatever plus 1 over n minus 1 plus 1. Or plus 1 over n. You factor it out, it becomes 1 over n. Okay. And that's the answer for the first part. So the second part says, if the child has collected n coupons, what is the expected number of distinct coupon types? So I'm just gonna like copy this, bring it back down. Okay, so if the child has collected n coupons, what is the expected number of distinct coupon types? So if he has n coupons, how many of them are unique? Okay, so we're gonna say to obtain any particular coupon type, we have like n of them, right? We can have like, so that's like total, right? We can have like n1, that's like one of the types, n2, n3, n4, and it's saying the probability of obtaining, let's say n4 in particular, on your next poll is 1 over n. Because like, yeah, it's like there's n possible coupons, and you want to obtain, let's say n4, just n4 on your next poll. It'll be 1 over n. The chance of not getting it, right? Chance of not getting n4 is going to be 1 minus that. So probability, and n4 is an arbitrary number, an arbitrary pick, it doesn't matter, it can be any of them. Probability of not n4, so n4 complement, will be 1 minus that. And so now we're trying to say the chance of not getting n4 across all n of your possible picks will be chance of not getting it, right? Times not getting it again, times not getting it again, and so on, right? N times, lowercase n times. And so since it's independent, you can just multiply the probabilities, and you get the probability of not n4 in n tries is 1 minus 1 over n the power of n. And n4 is arbitrary, so we're saying the probability of not getting a particular coupon in n tries is 1 minus 1 over n to the power of lowercase n. And so the probability of getting a particular coupon, like in your n tries, is 1 minus all of this. So probability of n4 complement, of not getting n4 in n tries is that. So probability of getting n4 at least once, right? That's the reason we're doing this whole complement stuff, is to get the cases for like, oh, we can get it once, twice, 3 times, right? We're trying to see the probability of getting it at least once. So to do like the at least once case, you have to do 1 minus not getting it and that way you cover the chance of getting it across once, twice, 3 times, 4 times, 5 times. So probability of n4 in n tries, or n4 complement in n tries, all of this complements to the opposite of this, and therefore, which is the same thing as n4 in n tries, at least once, is 1 minus 1 over n. Sorry, 1 minus and then 1 minus 1 over n to the power of n. That's the probability of getting a particular coupon type at least once in n box openings. And so we're trying to find the expected number of coupons we're going to obtain. And so you multiply that by how many coupons you have, or you can possibly obtain. And so your final answer, the expectation, is going to be 1 minus 1 over n to the power of n, and all of that times n. The reason that you do times capital N is because you're saying the probability of getting at least one of them, right? But you have n possible ones you could possibly get. And so capital N possible ones you can actually obtain. And so that is the final answer.